Hi everyone. Let us wait for another 5 minutes for all others to join us. Just to let you know, this video is being recorded. Please be aware of that. Okay, since most people is already here, let us begin our lessons today. You have watched the pre-recorded lectures earlier. This one is just a recap of some important points on that pre-recorded videos, and you are free to ask any question anytime. So today we talk about Laplace transform again, and then we start with the Laplace transform table. And these tables, you can easily find similar tables from the internet, and you can also download the table from the formula sheet that I provided in Times. All right, please download the updated table because only last week I noticed that there's some typo in the table, so I've updated it. So please download the correct one. If you download it now, then it'll be the updated one already. All right, so usually what we do for inverse Laplace is that we refer to the table itself without finding out the, without doing integrations to find out the final answer. So by referring to the tables, we can easily obtain the answers. For example, let's say you just refer to 1 over s squared, you will see that the answer is actually t multiplied by ut. Hey, somebody say you cannot join. Okay, hold on now. Let me meet him first. Okay, so similarly for others form, let's say you have s over s plus 1, where you cannot find out this particular inverse Laplace from the table. What you can do is that you can make it a proper way. Proper way meaning that you have numerators over denominators, right? Usually you can find the inverse Laplace if your denominators has higher order than numerators. All right, so it need to be higher order, meaning that let's say the numerator is s plus 1. Your denominator has to be s squared plus 2s plus 3. Then you'll be able to find out the inverse Laplace transform from the table itself. If you have both with the same order, let's say s plus 1 and s plus 2, then you cannot find this answer. So you have to do kind of like factorizations. So you write s plus 2 minus 1 with s plus 2 and make it 1 minus 1 over s plus 2. And then you find individually each of these, the inverse Laplace from the table. All right, so these are, I've explained in the videos already. So I'll go to the next one. So now if you have let's say another functions with denominators has more than the s. So if you look at the Laplace transform tables, sometimes you can have the s squared plus a squared over a squared, over a, sorry, and then this will give you either cosine or sine, I forget one of it, all right? Then, but sometimes you cannot get this kind of form, but you get like s squared plus 3s plus 2. And at this time, you will need to split your functions into two parts, especially when you can factorize the denominators of the functions. This is a wrong example, so please don't look at this example. I give you another example. S plus 4 over s squared plus 3s plus 2. In this case, if I ask you to find the inverse Laplace, you can't really depends on the table itself. So what you can do is that you can break this down into two parts. One is s plus 1, you just factorize it. One is s plus 2. And then by factorization, you'll be able to find out these two individual terms. And this is called the partial fractions expansion. So sometimes I just write PFE. All right, so in today's lecture, most of the time you will need to learn on how to do partial fractions expansion. So which is to break out, let's say, systems with two denominators, factors, to break out into individual subsystems like this. So let us look at some of the example. Okay, so for this example, let me check if I have any other example. Right, this is the first case that you will encounter, which your denominators can be broken down into two different factors. And this is one of the easiest case. So you just need to split both the factors up in this way. And then you multiply the factors up to the left side, meaning to here. So you get the 2 on the left side, and right side is a multiplied by s plus 2 plus b multiplied by s plus 1. And now you can substitute any random value. Now you can substitute any random values to find out what is the a and b for s. So an easy way to do that is to substitute a value of s so that either one of it becomes 0. So there are two terms here, right? So let's say I want to make this term to be 0 first. So s equals to -1 will make that term to be 0. Then I substitute -1 into this first term, I get a1. So a is 2. Sorry. Then the next one, you do the same thing on the other side. Now you write s equals to -2 to make this to be 0. Then you'll be able to find out your b. So ultimately, you will have your final answer. Let me clear the screen here, a bit too messy. You have the final answer, which is equals to 2 over s plus 1 minus 2 over s plus 2. All right, because you have found out what is your a and what is your b. And then each of them, you can find out the inverse Laplace. For this case, it's just 2e negative t. And for this case, it's 2e negative 2t. So you get your inverse Laplace transform this way by referring to the table. All right, this one is still referring to table. But each individual terms you can find on the table now. So we go to look at a more difficult example. So this second example, it has not only difference root, it has a root that is repeated also. So if you have roots that repeat, then when you break down your system into different subsystems, this one, you just follow back the similar methods. Any difference root, you will just be a difference term itself. Hold on, I let Zil come in. Zil keep disconnecting, I think. All right, and then the repeated root itself, you will need to have an additional terms on the repeated root, which has the squared number here. So this is not just squared. Let's say if you have terms such as s plus 2 power to 3. So we don't bother what was on top. Then you need to break it down to s plus 2 plus b, s plus 2 square plus c, s plus 2 cube. All right. So when you have power to 3, you will need all power 1, power 2, and power 3. When you have power of 2, like you see here, you will need power 1 and power 2. That's all. So this is how you can break it out. And after you can break it out, you apply the same methods to find out what is your ABC. So you multiply everything up, you get A, s plus 2 square, plus B, s plus 1, s plus 2, and plus C, s plus 1. Then you substitute s equals to certain number. Then you find out what is A. Substitute s equals to certain other number, find out what is B, and then C. Right? So the procedure becomes the same. Only that when you break it down into different subsystems, it is different. Right? So this is case number 2. So what if we have case number 3, which is the last case here, where you have a term that cannot be factorized. You cannot break these terms down into 2 different brackets. So for this kind of term, what you can do is that you split out whatever that can be factorized. S itself is a factor, and this one is the next factor. So you split out into 1 and 2. And then if you look at the denominators for these second subsystems here, this is of s squared. So when it's from s squared, your numerator needs to have s and non-s term. So something s plus something else. So let us follow back the alphabetical order. So this is B, S plus C. Right? So I give another example. Let's say if you have 1 over s plus 1, s squared plus 2s plus 3. This one you cannot break it down into 2 parts. Then it will be A over s plus 1 plus bs plus c over s squared plus 2s plus 3. Then you use the same methods to find out what is your A, what is your B, what is your C by trying different s value. Then after that, you find the inverse Laplace transform for each of the term. You should be able to find it. But when you have terms such as the s squared, then most of the time, you will need to use the, what is it called, the frequency shift methods. All right, or S shift. We'll look at it from the tutorials on Friday. All right, there are some questions on this one if I'm not mistaken. Okay, so to solve this one, it's the same thing. You just multiply everything by the denominator, and then you form the equations. You let s equals to certain number, and then you find out what is A. S equals to something else, you find out what is B. S equals to something else, you find out what is C. So this one is quite trivial. Okay, so next, I remember a few weeks ago, somebody asked me about zeros and poles. So that is where you are going to learn here, but not much of it. Is called transfer functions. So let's say you have a systems, and these systems has certain impulse response in time domain. And then you input the systems with an input in time domain, and then you get the output. Now, we know that the output from our previous lectures is equals to your input convolutes with your system impulse response, correct? That is how you get your input, output. Then we are saying that if we are able to take Laplace transform of each of them. So this one become ys if I take Laplace. This one become xs if I take Laplace. This one become hs if I take Laplace. If I able to take Laplace for each of them, these convolutions will become multiplication. Right? So that is how we can solve the output of a system easily. We just take Laplace transform, it become multiplications, and then after we multiply them together, we partial fractions it, and then we take inverse Laplace transform. Then we can find out y again. So now, let us look at this h. We have ys equals to xs multiplied by hs. And therefore, this hs, if you do around with mathematics, is just ys, which is the output, divided by input. So this one, if I write it down, is output divided by input. And this thing, they have a name for hs. They call it as a transfer function. All right, a transfer function meaning that in Laplace domain, in S domain, is the outputs of the systems divided by the input of the systems. And that is called a Laplace, that is called a transfer function for that systems. So we can use a transfer function to represent the systems. All right, let us look at the next. Okay, before we go there, all right, this one I didn't say in the slide or in other things. So let's say you have your transfer functions. I've talked about this one because somebody asked me about pole and zero last time. So let's say you have transfer functions, you have output divided by input, and it is always in a polynomial divided by polynomial form. So let's say it's s squared plus 2s plus 1 divided by s cubed plus 3s plus 6s plus 9, something like that. Let's say this is the example. Your transfer functions happens to be this form. So in these transfer functions, you have numerators and you have denominators. The definitions of zero and pole, which you see it, I think in one of the tutorial earlier, which I mistakenly written it down, is that zero is the numerators equals to 0. Pole is the denominators equals to 0. So what do I mean by here? So numerator equals to, it means s squared plus 2s plus 1 equals to 0. So I can factor this, s plus 1 equals to 0. So s equals to -1. So this -1 is my 0. All right. -1 is my 0 in this case. So pole is when denominator equals to 0. All right, and then you try to solve this into 3 different things, and then it will have 3 different poles. All right, most of the time, or I would say all the time, the number of zeros and the number of poles depends on the power that you have on the numerator and denominators. When your power is 2, then you have 2, either 0 or poles. All right, if it's numerator, then it's 2, 0. If it's denominator, then it's pole. So in this case, if you look at this example again, I actually give a quite bad example because both s equals to -1. They are actually 2 zeros, and both zeros are at -1. You have to write it this way. Both zeros are at -1. But actually, you will not need to use any concepts of zero and poles in this lecture or in this course. You will use it in automatic controls and real-time instrumentation, that particular modules. You will use a lot on concept of poles and zero. But now I just let you know since somebody asked me this question last week. Okay, any more question on pole and zeros?
Sir.
Yes.
Just want to ask, like, what is the uses of knowing zero and poles?
Okay, very good questions. A question that I like to answer because it's related to control systems. So, what is the use of knowing zeros and pole? I will talk about pole first. First, I tell you about why is it called zeros and why is it called poles. If you plot this out, this is a polynomial against another polynomial. Let's say s plus 1 divided by s plus 2 and s plus 3. if I plot this HS out, I will get certain signals. I'll get certain signals. And okay, this is S plus 2, S plus 3. Yeah? So I am -3, -2, and -1. At -3, I get infinity value. This is infinity. At -2, I get another infinity value. At -1, I get a 0 value. And then all others remains some other random value, which I don't even need to calculate. So you see, when this one equals to 0, mean S equals to -1, your HS will become 0, right? That's why the value is 0 here. When S equals to -2, your H -2 will become infinity, right? That's why you have infinity here. -3 will give you infinity as well. So that is where the names come from. You see, when it's 0, it is called 0. When it's infinity, if you plot the graph out, you will see a pole like this that goes up to infinity. So that's why it's called pole. So first, this is how the name comes from, poles and 0. All right. Then next, I will talk about what is what is it so useful about poles and 0. We talk about pole first. Pole will determine on how your system behave. All right, let's say I give an example. Yeah, the system is here. Let's say I have 1 over S plus 1. And then this XS is 1 over S. So it means that my XT is actually UT. So my XS is 1 over S, correct? Because UT, you do Laplace transform, it becomes 1 over S. So what is your YS? Your YS is 1 over S multiplied by 1 over S plus 1. And if you do partial fractions, this becomes 1 over S minus 1 over S plus 1. Okay, I did it very fast, so I know it. But you can do it slowly, you get the same answer. Then what is your inverse Laplace? This becomes 1 minus e negative t. All right, now you imagine your S is S plus A. All right, a general S plus A. This is a pole. Your pole location change. Instead of -1, now become -A. So you have A here, and then the whole thing become 1 over A S plus A. Then what is your YT now? Your YT become 1 over A, 1 minus E negative AT. So if you plot the two graph out, we can ignore this 1 over A because it's just a scaling gain to your system. But this is the dynamic part. Dynamic means the system changes. If you plot it out, the red color one, which is S equals to 1, looks like that. And the blue color one, S equals to negative AT, looks like that. All right, the bigger the A is, the steeper is this curve. So you see, your pole locations actually determines how your systems behave. All right, some system behave it like this. Some system behave like this better. Some system behave very good like this. And it is determined by your pole location. All right, when you give it a constant input, let's say this is the input that you give. Then you input at time t equals to 0. So for 0, it will not, it will affect your systems, but it will affect your system randomly. It depends on different systems. You cannot have a generalized says that, okay, if I have 0, the system is better, or if you have no 0, the system is better. You can't say that because we don't know yet. It depends on system to system. But for pole, we can say, if your pole is more negative, meaning that let's say you have S plus 100. You compare with S plus 1. These S plus 100 systems will behave more agile compared to S plus 1 system. Because S plus 1 systems, it rises up very slowly, like this. S plus 100, it rises up very quickly, like this one. All right, so this one is more agility. So meaning that if you apply this is your car, meaning that your car can pick up faster. If this is your car pick up very slow. So usually when we design a systems, we want a system to have a very negative pole so that the system react faster. All right, but you only learn this in control system later, not in this course. Does that answer your questions, Kin Long?
Yes, thank you, sir.
Okay, no problem. Okay, so we have certain properties of transfer functions or certain properties of Laplace transform is that we can easily do Laplace transform on different dynamics. You want to ask something, Kino? No, right?
Yes. Sorry to interrupt, but I wanna know like how LTI actually affects the transfer function. I've listened to the lecture's explanation, but not really clear with that. Still a little bit confused.
Okay. You see, when you break down a system, okay, I give you one example. This example, when you break down a system, 1 over s plus 1 equals to 1 over s minus 1 over s plus 1. Then you apply Laplace transform, you get 1 minus e negative t, correct? You are actually applying Laplace transform on a new system. You apply on 1 over s, and then you apply on 1 over s plus 1, and then you add them up together. This only happens when you have a linear system. If you have non-linear system, you cannot add them up together. So the whole transfer functions definitions are based on this kind of assumption that we do. We break the system down into many, many systems, and then each of them we do the Laplace transform, and then we add them up together. So that particular, this system must be a linear system to start with. If not, you can't even find the Laplace transform of it. And then it must be also time invariant systems, meaning that your system will not be affected by time, the time that you apply to the systems. So can't really explain this one well, but then Laplace transfer, these transfer functions, it is said already, they only works in linear and time invariant systems. It doesn't work on non-linear system and doesn't work on time variant system. Okay?
Sir,
yeah.
If that is the case, right, can Laplace transform works on other system as well, like maybe time varying system?
Laplace transform cannot. Let me think. Laplace transform, non-linear system definitely cannot. For time varying systems, this one I need to check. For time varying system. But my suspicion is cannot. Because time varying systems, you have the time that you apply on the system is different from when you apply at a different time. I suspect Laplace transform cannot do that. Can't apply on that. But I'll go and check it out and I'll let you know.
Which means Laplace transform can actually only works on LTI system?
Yes. Yes, correct. Only works on LTI systems.
But I mean, it's most of the real life application is LTI system.
All right. Most of the real life system is not LTI systems, but we always approximate it to LTI systems. All right. This is a not say set truth, but this is what engineers like to do. They like to simplify a system, because if you have a system that is non-linear, non-time invariant, there is no way you can understand the systems. Let's say you have a pendulum systems. I think I talked about these examples. When this pendulum is swinging, this is actually a non-linear systems. You will see the graph of pendulum swing to be something like, if I'm not mistaken, it's something like this. Right, this is supposed to be 0. Let me draw properly. But what engineers like to do is that they always like to draw an approximation line. And then if you look at this approximation line and the blue color original line, you notice that they both look alike at this region. So this region, they call it the linear region. So what they can do is that they approximate this particular non-linear pendulum system into a linear system. And then they apply all this Laplace transform to find out what is the performance of these systems, etc. But they know that that performance of these systems only happens when your angles is between these two particular limits. Because you see, between these two limits, the blue color curve and the red color line are matched very well. So that they call, this process is called linearizations. Right, it's called linearization. So most of the real world examples are not LTI, but they are always be approximated as LTI so that we can proceed to analyze them.
Right, understand. Thanks, sir.
No problem. Okay, so this is the transfer functions, which I mentioned earlier. It always consists of numerators of a polynomial of S and denominators of polynomial of S. Okay, so this is examples of how you can find a transfer functions of a particulars from the particulars mathematics equation. So this is actually the input to the system, and this is the output of the system. And the output of the system is governed by this equation. So what you need to do is that you just directly take Laplace transform of each of these terms. Because it's LTI system, you can take it one by one. So y dot become sy, 2y become 2y, and x just become back x. And then your transfer function is output versus input, remember. So it's always y over x. Then you get 1 over s plus 2. Now you can easily analyze your system already, because you know that ys is 1 over s plus 2 multiplied by xs. So what is your input? Let's say your input to the system is a step input, ut. So in Laplace, it's called 1 over s. So this one will become 1 over s plus 2 multiplied by 1 over s. And then you do partial fraction, it becomes 1 over s minus 1 over s plus 2 divided by half. Then you do inverse Laplace. After you do inverse Laplace, you get half of 1 minus e negative 2t. Then you can even plot the output out. This output will look something like here, and this is half. All right, and then your input is a step function. So your input is the green color one. Your input is actually this. This is your input, and your output behave like that. Okay, so that is how you can find out a transfer function given the dynamic equations of your system. So this is called the dynamic equations of the system. All right, here are some of the way that you can simplify transfer functions. So we know that the output, let's say this one is x1s. ys is h2s multiplied by x1s. And we know x1x is h1s multiplied by xs. Then we can just substitute it into that. So we get ys equals to h2s multiplied by h1s multiplied by xs. But now you look at this one. If you look at this as a single system itself, it is still valid. This is the input, this is the output. Output equals to a transfer functions multiplied by the input. So we can make a conclusion saying that these two systems connected in series is actually same as one system that is just a multiplication of both the systems in transfer function. Right? Meaning that let's say I have a system that s over 1 over s plus 1, and then it go through 1 over s plus 2, and then only come out output. This is same as a system that go through 1 over s plus 1, s plus 2. So sometimes you see complicated block diagrams, many blocks together. You can simplify them by just multiplying them together. The same concept happens here. When you have parallels, you just do the mathematics like what I did earlier. You'll notice that you can also find an equivalent transfer functions that is just h1 plus h2, all right, if they are added up together. The next, for feedback case, you still, you have watched my lectures. I should have solved this already. So again, the same thing, you just play around with mathematics. Ys equals to f multiplied by e. I just lazy to write the s. then E equals to X minus R, and then R equals to G multiplied by Y. And then you solve this equation, you will get this transfer function. So meaning that although this particular looks very complicated, you can easily find an equivalent transfer function that represents this. And why is it specifically I talk about this loop? Because this is a very classical closed loop system, or sometimes they call the feedback control system. All right, this is the feedback. And controller, sometimes they put it here, or sometimes they put it here. All right, oh, this one I write controller to be here. Okay, then the systems is over here. But you need not to worry about that for now, because you only use it in control systems later when you study the next module. Right, this is a very famous feedback loop. Most of the time, feedback loops will look like this. There are 3 blocks, not just 2 blocks, okay? All right, the third block is here. So this is the controllers, this is the system, and this one is the sensor feedback. All right. Okay, 2 very important theorems that you can use to find out the initial values or final values of certain signals. Let's say you have a signal. Let me think. Let's say you have a signals. Okay, let's say we have this system. This xt, this one is yt, and this is 1 over s plus 2. Now, I know that my xt is actually ut, a step function. So this one in Laplace domain is 1 over s. So I'm asking you, what is the first value of y and what is the last value of y? Meaning that my y, remember in this kind of system just now we draw, it will start from here and then it will end out on certain value. So what is this first value and what is this last value? So this initial value theorem and final value theorem tell us that. So how to apply that? So what we do is that we need to take the Laplace transform of the output. So Laplace transform of the output is 1 over s multiplied by 1 over s plus 2. Now we don't need to solve this. We don't need to find out partial fraction and inverse Laplace. What we need to do is just to apply these 2 formula. For this question, if I apply initial value theorem, it's quite useless because it always starts with 0. So let us apply final value theorem. So final value theorem tells us that y infinity is limits of s close to 0, s multiplied by ys. So in this case, s close to 0, or I shouldn't draw a line here, s multiplied by ys is s multiplied by 1 over s multiplied by 1 over s plus 2. So you notice you can cut off these 2 because they are the same. And then you substitute 0 into s. So you get 1 over 0 plus 2, which is 1 over 2. So you know this particular value is half. Your y will go to half when the time is infinity. So y infinity is half. So that is how you can make use of final value theorems. If you want to solve using Laplace transform, also okay. You can also find the final value. So let us solve it. This one, if you use a partial fraction, it becomes like this. All right, if you do partial fractions, you will get this answer. And then if you do inverse Laplace, you will get this answer. Half of 1 minus e negative 2t. So when y infinity, you substitute infinity to it. 1 minus e negative infinity. E negative infinity is 0. So it's half multiplied by 1 equals to half. You see, you get the same answer. But these theorems kind of like allowing you to find the answer quickly without solving this. This particular example is very simple. It's just 1 over s multiplied by 1 over s plus 2. What if your transfer function is something like this? S squared plus 3s plus 5 divided by s cubed minus 4s squared plus 2s plus 1. And then it's very difficult for you to do the partial fractions. And if you are required to find out the final value or the initial value, you can just make use of this. Very simple. Okay, I think that's all for the class today. Yes.
For this initial and final value theorem, right, is applicable for input and output, is it?
Applicable for any signal actually. For any signal. So let me try with another signal. Let's say I have a signal that is UT. All right, so my signal is UT. UT like this, right? You remember UT is go up. So final value is always 1. Initial value is 0. But actually you cannot find initial value here because at 0 it goes to 1. Most of the time nobody will use initial value theorem. Final value theorem is used very extensively. So let us look at final value. In this case, what is UT is UT. If I Laplace it, it becomes 1 over S, correct? When it becomes 1 over S, I substitute into the final value theorems. So x infinity equals to limit of S to 0, S multiplied by 1 over S. Then you cut this off, 2 off, is equals to 1. You get the answer already. So it's equals to 1. You get it? So let's say if you have other value, let's say you have a sine or cosine value, sine t. Sine t has no final value because why? Because it keep going up and down. There's no final value at all. So I don't think you can find answers if you use a sine t. But sine t, if you take Laplace, is what? S over S plus S squared plus 1, right? Something like that. I forgot what is the Laplace of this. Need to refer to the table. And then if you apply to this one, you substitute 0 into it. I don't think you can get a final answer for this one. So only certain case where you are sure that you can get final answers, the final answer is indeed, it will go to one answer, then only you can apply final value theorems. And yes, you can apply to signals. But I can't really give you another examples that signals that go to only one point. So most of the time, people apply on the outputs of a system. So they apply it here. So they given you a input and a impulse response, and they ask you to find out what is the final values of this output. Then is very useful. Okay, any more questions? Right, if no questions, actually today I wanted to discuss about your lab as well. Because you are supposed to start working on your lab 2 this week. And let me share the lab. So for lab 2 is very similar to lab 1. Lab 1, you were working on Fourier series. And in lab 2, you are going to work on Fourier transform. All right, so in lab 2, all these theory are just like the usual theory. Just read through it. It's similar to what I wrote in the lecture slide. And then 4 is where you really start working. So the same thing, you find the Fourier transform of this particular signal. You should be very expert by now to find Fourier transform of this one. And manually using your hand calculations, meaning that you apply this formula to find out what is the Fourier transform, and then sketch the amplitude spectrums of your Fourier transforms output. So this one, do you remember? Rectangle functions, after you do Fourier transform, it will become the sinc function. Remember the function that looks like that. So you are going to get this function later on. So you need to sketch it out manually on the either graph paper or just sketch it on the empty white space, as long as you label clearly all the crossover frequency, that's all. And remember, amplitude spectrums is always positive only. All right, amplitude spectrum meaning that you have to get the amplitude of that particular signal. So instead of going down, your signal should look like that. All right. And then now you need to use MATLAB to plot it. Your amplitude and phase spectrums of this signal. what you need to plot is that you have found out your Fourier transform from 4.1, right? Then you use the equation that you found out and then put into MATLAB to ask MATLAB to plot exactly this graph out. All right, and then there are certain conditions. The first condition is that to plot this graph out from 0 or 0.1 to 20 radians per second. Then the second question, the 4.4, asks you to plot it out from 0 to 100. All right, 0 to 1,000. 100 radians per second. All right, and then we'll ask you what is the impact of plotting with different range. Right, and then you need to answer these questions, that why you need to use term, which I already asked you to answer in the last lab actually, but in this lab you answer it again, why you need to use term instead of using plot in periodic signals. And for this particular signals, you have to use plot, all right, because this is a continuous signals. You only use term in discrete signals. Okay, and also to work on this particular lab, I'm not sure whether in your lab manual did I write this too. Okay, you first use A equals to 1 and tau equals to 1 to find out to work on this 4.1 to 4.5, and then you use A equals to 2 and tau equals to 2 to work on it, and then both answer you need to plot out for me. All right, so you have two sets to do this. One set is second set. Okay, and then your lab reports again you submit on next Sunday. All right, I give you 1.5 weeks to work on this one. So next Sunday you need to submit to turn it in times. So any question you want to ask about this lab?
Sir.
Yes.
What does it mean by 1,000 samples?
Okay. Do I have empty space to write? Okay.
Is it same with the one in the tutorial?
Sampling. No.
Explain.
This one is not really talk about sampling theorem. What I mean here is that 1,000 sample. Okay, you see, between 0 to 0.1 to 100 in MATLAB, right? When you want to define this one, let's say it's a frequency axis, and this one is the amplitude. MATLAB is a numerical computations. You cannot just say T equals or F equals to 0 to 1,100. You have to define F equals to 0.1, 0.2, 0.3, all the way to 100. So that is what it means. It has total of 1,000 samples, total of 1,000 points. You get what I mean? It's
yeah, I get what you mean now.
Okay, you got what I mean already, right? So you need to write a MATLAB code to generate this number, 0.1 to 1,000, to 100, where it has a total of 1,000 numbers.
Understand?
Yeah. So it doesn't not related to sampling theorem. Don't confuse by it. It's just for MATLAB to generate the axis. If you have any more questions on lab, you are free to ask me in WhatsApp this week or next week. But please don't drag until the last 2 days where it is weekend, because weekend I might not reply in time. Okay, please ask during weekday. Okay, any more questions? If no, I think it's almost time's up also. It's about 6 p.m. already. So I will see you guys on Fridays to talk about, to discuss on tutorial. But please work on the tutorial. I will give you about half an hour on Friday, 2:30 to 3 p.m. to work on the tutorial. I will not disturb you that time, but 3 p.m. onwards, we'll discuss on the tutorial. I hope all of you work on the tutorial before we discuss, so that you all know what's happening, not just listening to the answer. You will not gain anything by listening to answer only. All right, so I'll see you guys on Friday, 3 p.m. You all can leave already if you have no questions. If you have questions, you can stay on and ask me questions.
Sir.
Yes.
Just want to ask, for the Laplace transform table, right? Okay, yes, we have learned Laplace transform before, and we have actually used the Laplace transform table before in the mathematics, but it's different with the one in signal, which it has actually another step signal behind of every transform. I mean, behalf of every original signal.
Okay. In signal and systems, or later on when you learn about control systems, in mathematics, it talks about, it's just mathematics. Like, it doesn't relate to real world examples. But in signal and system, what we need to do is that we need to relate all these signal and system into real world examples. And in real world, there is no signals or system that is having future value. So all signals will start at time t equals to 0. That's why everything I put a ut over there. It's just to tell you that the system or the signal start at time t equals to 0. It doesn't start before t equals to 0. It doesn't start at negative time number, because in real life there's no negative time. So that is the reason for that. But they are actually the same, whether you put a ut there or not.
Okay.
Yeah.
So also, when I ask for inverse Laplace transform, right? Is actually integrating from negative j infinity to j infinity.
By right, if you use the formula, yes, you need to do that.
Like the j infinity, the concept of it is kind of confusing.
Let me check. Hold on. So basically, for inverse Laplace transform, I don't even see any possibility that asks you really integrate it. So most of the time, I would say 99.99% of the time, you are actually need to refer to the table. You will not integrate it. So you don't have to worry about the integrations from j infinity to infinity. If you really want the integration from j infinity to infinity, you just substitute your t or your s to be j infinity and negative j infinity. But I doubt you'll be able to solve it using the integrations. I will say just refer to the table. Do not use the formula. Later on, the next chapter, when you learn about Z transform, you'll notice the inverse Z transform is even worse. It's the surface integrals of certain values, where you never even heard of what is surface integral. Or not surface integral, it's a contour integral. So it's an integration with a 0 inside the integration. So don't worry about all these mathematics. For inverse Laplace and inverse Z transform, just refer to the table.
Okay, thanks, sir.
Okay, no problem. Actually, I'm looking at the internet now. Most of the teaching materials in internet that talk about inverse Laplace doesn't even show you the formula. It just asks you to refer to the table. So just don't worry about that. I don't think anyone actually use the formula to find it.
So also one last thing I want to ask is regarding to the case study. Is there any latest news about it? Just want to know.
Case study, okay. The latest news that I know might not be the latest for the real thing, is that week 12, it will be released to you guys.
And we are given 4 weeks to do, right?
Yes, about 1 month time, if I'm not mistaken. So after 1 month, you need to submit it. I think you will need to submit all the modules together. So meaning that although you are giving 1 month time, doesn't mean that you have the whole 1 month time to work on this module only. You actually, this whole 1 month time, you need to work on all the modules that you took. All right, so please don't drag until the last minute.
So I have heard about this semester is not counted in for the CGPA and some rumors about it.
I never heard of this. All right, I never heard of this, so I'm not sure whether it's true or not. I have not heard of this one, or I have not given instruction about this one.
All right.
So I think the best person to ask is Dr. Arabin.
Okay. All right. This is week 9, week 10.
Today is week 9.
So week 12 hours, do we actually have a lecture or tutorial session?
On week 12, we do have 1 lecture and 1 tutorial. It's on the last topic, but that is the last topic already. Week 13, there's no more lectures or tutorial on week 13 and 14.
So week 14, we only do the lab test, right?
Correct. And then your lab 3 will be, I forgot which week I put it already, but somewhere around there.
Week 12.
Did I put on week 12?
It's not mistaken.
I told you on week 12, is it?
Yeah.
Check. Because I have too many modules that I don't really remember all the labs week. I try to separate all the labs week so that I'm more free to mark your labs. Let me check. Signal and system is on week 12, correct? So week 11.
Week 11, okay.
Week 11, right? Lab 3 on week 11, which is 2
Yes,
weeks from now. So on week 11, you will need to do lab 3, which is on Laplace transform, what you have learned today.
Sir, can I know the lab test will be on Wednesday or Friday?
I have not decided yet. I leave it down to majority of you, whether you guys want it on Wednesday or Friday on week 14. Okay. Because for me, both slots are free for me. I need to make sure all students are free in that slot that you all chosen.
So does it mean that for all modules that we took this semester, everything will be done on week 12, and starting on week 12, we should start working on the case study?
I don't get your questions, but what I can tell you is that all modules will release their exam papers, final exam, case study on week 12. And then
it is confirmed.
At least for now, it's confirmed. But you know, this a lot of instruction keep changing nowadays because you know MCO suddenly stop, and then maybe student can go back to campus. I don't know. So maybe there are still changes. But current instruction is that week 12 we release case study to you. And then modules that haven't finished teaching by week 12, they will still continue teaching on week 13. It depends on the lecturer whether they want to teach or not. So we are given choice whether we want to squeeze everything by week 11 or week 12, or we continue as usual like week 11 or week 12. But for signal and system, there is no week 13, only week 12. Week 12 is the last lecture.
Oh, okay. So it actually depends on lecturer.
Yeah,
to choose one to release on week 12 or not.
To release is the compulsory thing, meaning that everyone will follow the same instruction. If it's week 12 release, everyone will release on week 12.
Okay.
Or for lecture and tutorials and lab is down to the lecturer itself. So maybe some lecturer even have lecture on week 14, maybe. It depends on the lecturer.
Understand. Thanks, sir.
Okay, no problem. All right, others, if no questions, then I'll see you guys on Friday. Thank you for joining today. Bye-bye. Oh yeah, before you go off, those who haven't do the TES for me, please work on it because I need at least 75% of response rate. Currently, it's only 40% of you have done it. So those who have not worked on the TES, please just log in and then just vote for me. Thank you so much. So I see you guys on Friday. Bye-bye.